Let's take a look at example 4. Suppose we have the differential equation x cubed y triple prime minus 2xy prime plus 4y is equal to 0. We are told that y1, which is equal to x squared, and also that y2 is equal to x squared the ln of x, are solutions on the interval 0 to infinity. So again, it's important to kind of keep in mind, because that right hand side is 0, that means that we are working with a homogeneous differential equation. It's a homogeneous linear differential equation. Furthermore, it's of order 3 because we have the y triple prime. According to the superposition principle. So according to superposition then, this would imply that y equals some constant times y1 plus some constant times y2 would also be a solution to this differential equation. Let's actually go ahead and verify and check this. So this is going to be quite a bit of work, but let's do it anyway. So we need up to the third derivative of y. Let's go for that. Y prime, if we do the first derivative, that's going to be a 2c1 of x plus, now be a little bit careful here, c2 x squared ln of x. This is going to be a product, so we're going to need to do the product rule. Let's associate c2 as being with the x squared, and then we'll think of the ln of x as being the other term. The derivative of c2 x squared would be c2 times c2x, leave the ln of x alone, and then plus you're going to have c2 x squared, leave that alone, but the derivative of ln of x is going to be 1 over x. So we can simplify our first derivative here. We get 2c1x plus 2c2x ln of x, plus this will simplify to c2x to the first. And if we notice, we can actually kind of combine these two because those are like terms. So what do we have? We have, factor an x out, you have 2c1 plus c2 times x plus 2c2x ln of x. Let's now take the second derivative by differentiating this part. The derivative of a constant times x is just going to be that constant. So we get 2c1 plus c2 plus, once again, here we're going to have a product rule. Thinking of this as, let's say, the constant 2c2 times x is the first piece, times the ln of x. The derivative of 2c2x is going to be 2c2, leave the ln of x alone, plus, now we're going to leave the 2c2x alone. We're going to multiply that by the derivative of the ln of x, which is 1 over x. These x's will cancel, so that will give us 2c2, which we can combine with this constant here. So we have 2c1 plus essentially 3 c2s. We have 2 here and 1 here, plus 2c2 the ln of x. And now we're going to go for our third derivative, y triple prime. This is a constant, so its derivative is 0, and this is a constant times the ln of x. The derivative of the ln is simply going to be 1 over x. So we now have our function, and we're going to try to plug this y equals into this differential equation and see if indeed the superposition principle gives us what we think it should. We know that this should be a solution. So I don't need the second derivative for this. I just need y triple prime, y prime, and y. So let me try to delete what I don't need so we can get some space. So my y triple prime at the bottom. This thing here was y prime. Y prime was 2c1 plus c2x plus 2c2x ln x. And then this this function here is what we claim is the solution. So let's check this. We have x cubed times y triple prime. This is 2c2 over x minus 2x times y prime. Y prime is 2c1 plus c2x plus 2c2x ln of x, and then we have 4 times y, which is c1 x squared plus c2 x squared ln of x, and this is supposed to be equal to 0. Let's go through and algebraically simplify this thing. If we distribute the x cubed in, we're going to get 2c2 x squared. Let's distribute the negative 2x into this. I'm going to get a negative 2x squared times this coefficient 2c1 plus c2 minus 2x times this thing will give us a minus 4x c2, should be x squared, x and x give us x squared, c2 ln of x. And then we also have our plus, if we distribute the 4 in, 4c1 x squared plus 4c2 x squared ln of x should be equal to 0. And let's distribute that negative 2x squared in. We have 2c2 x squared minus 4 c1 x squared minus 2c2 x squared minus 4x squared c2 ln of x plus 4c1 x squared plus 4c2 x squared ln of x equals to 0. And now we cancel. So we have a positive c2x squared. We'll cancel with this negative 2c2x squared. We have a negative 4c1x squared. That'll cancel with the positive 4c1x squared. And then we have a negative 4x squared c2 ln x. We'll cancel with the positive 4c2x squared ln of x. And there we have it. So this function, which was obtained by the superposition of these two solutions, is indeed a solution to the homogeneous linear differential equation. So hopefully we don't have any doubt any longer to doubt the superposition principle. It certainly works. In this example, they also show that if you have a solution, that if you take a constant multiple of that solution, then that will also be a solution. So even more easily, if you look at y equals e to the 7x, that is a solution to the homogeneous linear differential equation y double prime minus 9y prime plus 14y equals to 0. Therefore, if you take a constant times that function, it too will also be a solution. So for different values of c, you can play around with it, but if c is 9, then you get 9e to the 7x, that's a solution. If c is 0, then you get the constant solution y equals 0, etc., etc. The next thing this brings us to is definition 4.11, which is that of linear independence or linear dependence. So let's suppose that we have a set of functions. We have n functions, label them f1 of x up through fn of x. These functions are said to be linearly dependent on an interval I if there exist constants c1, c2 up to cn. Not all of them can be 0, such that c1 times f1 plus c2 times f2 plus cn times fn is equal to 0 for all x in the interval I. Okay. Again, if you just trivially, if you use 0 for all of the coefficients, then of course that would obviously make the left-hand I equal to 0. But in the definition of being linearly dependent, you would need for not all of those constants to be 0. So at least some of them would have to be real numbers different from 0. And if you're able to find such a collection of constants C1 through Cn, then these functions would be called linearly dependent. Okay. If a set is not linearly dependent, then it is referred to as linearly independent. Okay. Another way that you can kind of rephrase this, it's equivalent, is that we would say that the set of functions f1 through fn, they're going to be called linearly independent on an interval I if the only solution to this equation is for constants where the constants are all equal to 0. So if the only time you have c1 times f1 plus c2 times f2 plus cn times fn identically equal to 0 for all x and I is when all of the coefficients c1 through cn are 0, then we would say that f1 through fn, that set of functions, is linearly independent. Let's take a look at a couple examples here. In example 5, they say that we have the following set would be linearly dependent. If we take the function cosine squared of x, sine squared of x, secant squared of x, and tangent squared of x, this function, this collection of functions is going to be linearly dependent on the interval negative pi over 2 to pi over 2. Okay. In order to see this, let's set this one up. So we're looking at the following. So f1 of x was cosine squared x, f2 of x was sine squared x, f3 was the secant squared, and I'll try to squeeze it in here, but f4 of x was the tangent squared of x. And we're claiming that this collection of functions is going to be linearly dependent on the interval negative pi over 2 to pi over 2. Okay. So to check this, what we would do is we would take and look at the following equation. You would take c1 times f1 plus c2 times f2 plus c3 times f3 plus c4 times f4, and we want to see if we can find a collection of non-zero coefficients, or at least not all zero coefficients, c1 through c4, such that this would be equal to 0. Okay. And I claim the following will work. Let's let c1 be 1, c2 be 1, c3 can be negative 1, and c4 can be positive 1. Let's go ahead and plug this in. That would give us cosine squared plus sine squared of x minus secant squared x plus tangent squared x would be equal to 0. And now we recall a few things from trig, right? If you remember from trigonometry, this is an identity. Cosine squared plus sine squared, that is equal to 1. And in addition to that, you might recall the identity from trig. This is a Pythagorean identity, that the tangent squared of x would be equal to secant squared x minus 1. So everywhere we see a tangent squared, we can replace it with secant squared x minus 1. The negative secant squared and positive secant squared cancel. The positive 1 and the negative 1 cancel. And so we get 0 equals to 0. Okay. So this equation is solved for these coefficients. So we found some values c1, c2, c3, c4, such that the constant multiples times those functions is equal to 0 for all x in the interval negative pi over 2 to pi over 2, which means that these functions f1 through f4 would be linearly dependent. So these ones would be linearly dependent. If you wanted to look at a set of functions that would be linearly independent, a classic example of this is just pick two x to the power terms that have a different exponent. These would be linearly independent. If you try to solve this equation, c1x plus c2x squared equals 0, for all x over the real numbers, well, the only way that, think of this as like a polynomial. So here's kind of the proof of this. So these will be linearly independent. So here's the proof. This thing in general would be some type of quadratic. So it's just, I guess, maybe a sketch of a proof. But you're going to have some kind of function x squared. Right? Now, what if c2 is equal to 0? Well, if c2 is equal to 0, then you would get a line. If we want a polynomial to be 0 for all x's, then essentially what you would need is for that polynomial to be flat, it would have to be the constant function y equals to 0. But the only way this thing would be 0 for all values of x is you would need for c1 to be 0 and also c2 to be equal to 0. So this equation is only true when both c1 and c2 are equal to 0. It's impossible to find a collection of c1 and c2 both non-zero to make this equation true. So we would say that x and x squared are linearly independent. So that's an example of two functions that would be linearly independent. If we wanted to look at another example of a linearly dependent set, we could take f1 of x to be the square root of x plus 5, f2 to be the square root of x plus 5x, f3 of x to be equal to x minus 1, and for f4 of x to be equal to x squared. This is entirely possible because we can write them as a linear combination. So in the book, if you notice what they're doing here, they're saying, oh, I can write f2 as a linear combination of the other functions. So f2 can be written as 1 times f1 of x plus 5 times f3 of x plus 0 times f4 of x. So how does that fit into our definition of linearly dependent? So the algebra portion of that, I'll let you kind of verify, but essentially what that means is the following. Let me take and subtract f2 of x from both sides. That'll give us 0 on the left-hand side, and now we have the following. I have 1 times f1 of x minus f2 of x plus 5 times f3 of x plus 0 times f4 of x. And these would be the coefficients we were talking about. So if you take c1 to be equal to 1, c2 to be equal to negative 1, right here, c3 to be equal to 5, and c4 to be equal to 0, we see that here's a collection of coefficients, not all equal to 0, such that c1 times f1 plus c2 times f2 plus c4 times f4 is all equal to 0 for all x in the interval 0 to 1, and that shows that these functions would be linearly dependent. Okay. So another way to think of it is if you can take any function in this collection, so here's an alternative formulation that's true. If you can take any function, or a function in this collection, here in this example we did f2, and if you can write f2 as a linear combination of the other functions, using all of the other functions, so if I can come up with an expression using f1 times some constant plus some constant times, let's say, f3, using all of them, then that's equivalent to showing that the set would be linearly dependent. The next thing we're going to come to is now we're going to look at solutions to our differential equations. And we are primarily interested in linearly independent functions or linearly independent solutions of differential equations. Although we could always apply directly definition 4.11, it turns out that the question of whether the set of n solutions, y1, y2 through yn, of a homogeneous nth order linear differential equation is linearly independent can be settled by using a particular type of determinant. And this determinant is what's called the Wronskian. So let's suppose we have again, we're focused right now on homogeneous nth order linear differential equations. And let's suppose we have this collection of solutions, y1 through yn. The reason why we care so much about linearly independence is if this set is linearly dependent, for instance, then what that would essentially tell us is that we could eliminate some of the solutions, and we won't have to write all of these solutions down because some of them could be obtained as linear combinations of others. And we know that via superposition, if we have a collection of fundamental solutions, then obviously their linear combination will also end up being a solution. So if this set is linearly dependent, then essentially we can remove some of them from the list and nothing would be lost. However, if the set is linearly independent, then in essence we have all of those functions are very important and cannot be derived as linear combinations of the other, and they would all need to be included and kept in our solution set. So let's suppose we have some functions, f1 through fn, that possess at least n-1 derivatives. We're going to set up the determinant, which is called the Wronskian. So the w of f1 through fn is formed by starting with the first column, will be the first function f1, and directly below it you write down its first n-1 derivatives. So row 1, column 1 will be f1, row 2, column 1 will be f prime of 1, row 3, column 1 will be f double prime of 1, etc., all the way down to the n-1st derivative. The second column will consist of the function f2 and all of its derivatives, up to the n-1st derivative, and we keep going across the rows until we come to our last function. The nth column of the first row will consist of fn, and that column contains all of the n-1 derivatives of the fn function. Okay. So this expression here is what's called the Wronskian. It's named after Józef Wronski, who's a Polish mathematician, and this will give us a way to check to see whether a collection of solutions are linearly independent. Suppose we have solutions y1 through yn are going to be the solutions to the linear homogeneous ODE, then this set of solutions will be linearly independent on I if and only if the Wronskian associated to those solutions, if that determinant is non-zero for every x in the interval I. So if that Wronskian is non-zero for every x in the interval I, then that collection of solutions is linearly independent. If the Wronskian is equal to 0 for some x's in the interval I, then these solutions would be linearly dependent. The book gives an example where they show y1 of x is cosine of 2 ln of x divided by x cubed, y2 of x is equal to the sine of 2 ln of x divided by x cubed. I'll let you show this on your own individually, but y1 and y2 both so happen to be solutions to this ODE. Furthermore, both of them happen to be linearly independent, because if you form the Wronskian of those two solutions, that determinant will be non-zero. Okay, that's going to be a lot of calculus and algebra to show that. Let me start with a simpler example. So let's take a look at, for example, this one here. If I have the homogeneous linear differential equation y double prime minus y prime minus 12y equals 0, we will take it with a grain of salt that y equals negative 3x, and that y2, which is equal to e to the 4x, are solutions to this ODE on negative infinity to positive infinity. The question we could then ask is, are these two functions linearly independent or are they linearly dependent? And to ask that, we're going to form the Wronskian. So we want w of y1, comma y2. So let's recall, how does this work? We start with the first function, it's going to be in column 1, and we need up to its first derivative. We're going to put y2 in the second column, and its derivative is going to go directly below. So if we have two solution functions, we need the function as derivative, because we're going to get a 2 by 2 matrix. So y1 was e to the negative 3x. The derivative of e to the negative 3x would be negative 3 e to the negative 3x. y2 is e to the 4x. Its derivative would be 4 e to the 4x. And now we need to find this determinant. You may recall from maybe a previous class, or if you had linear algebra, that if we have a 2 by 2 determinant, a, b, c, d, the determinant of this matrix is found by multiplying the main diagonal, a times d, and subtracting the product of the values on the minor diagonal. So it's AD minus BC is the value of this 2 by 2 determinant. So if we multiply this, I need to do e to the negative 3x times 4e to the 4x minus, on the minor diagonal, don't forget the sign in between should be minus, it's e to the 4x times negative 3 e to the negative 3x. Multiplication by like bases, you add the exponents. So that's going to give us 4e to the x. A negative times a negative will give us a positive 3. E to the 4x times e to the negative 3x will again be e to the x. And this provides us with 7 e to the x. And one of the things that we know is that e to the x is never 0. And so the Wronskian here of y1, y2 is non-zero for all x. In particular, it's non-zero on the real numbers, which implies that y1 and y2, so the functions e to the negative 3x and e to the 4x are linearly independent. So those functions are going to be linearly independent. If you have higher derivatives, so if you have, let's say, a 3 by 3 determinant, these can be evaluating using a process of what's called like a cofactor expansion. If we come across that, and if you need a primer on those, I can show you how to do higher order matrices as well. Most of the ones we'll stick to in this section will be the basic 2 by 2 ones, however. This now brings us to definition 4.13, which is the fundamental set of solutions. Let's suppose we have functions y1 through yn, which is a collection of linearly independent solutions of the homogeneous linear nth order differential equation on an interval I, is said to be a fundamental set of solutions on the interval. It's very important to notice the terminology here. It's said to be a fundamental set of solutions, not the fundamental set of solutions. All that's saying is that if you have these collections of functions and they're linearly independent, that provides us with one fundamental set of solutions. It's worth noting, and some of you might already be kind of thinking of this already, which would be fantastic, but we could ask the question, is it possible to form a fundamental set such that it contains functions of the form y1 and yn that are linearly independent solutions of the ODE, such that there does not exist any other function y that is a solution to the differential equation and would not be linearly dependent when added to the set. So in other words, we're asking, okay, if you're talking about the fundamental, like a type of like super fundamental set that would include all linearly independent solutions, we're not quite there yet. Okay, right now we're talking about a fundamental set being collection of solutions being fundamental set, which means that they are linearly dependent and they solve the ODE. The next thing to discuss is when we will have a fundamental set of solutions, and the good news is that there exists a fundamental set of solutions for the homogeneous linear nth order differential equation on an interval I. So for us, linear differential equations are nice. If it's homogeneous, it will have a fundamental set. We've already seen previously that at least y equals to 0 will be a solution, and oftentimes there's more non-trivial solutions as well. Analogous to the fact that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent vectors I, j, and k, any solution of an nth order homogeneous linear differential equation can be expressed as a linear combination of n linearly independent solutions on I. In other words, if we have n linearly independent solutions, let's call them y1 through yn, these are going to be the basic building blocks for the general solution of the equation. And so now here we come to the theorem 1.15. This is a very, very important one. Let's suppose that y1 through yn is a fundamental set of homogeneous linear nth order differential equations on the interval I. So we have these solutions. Then the general solution of the equation on the interval is going to be the linear combination of those fundamental set solutions. So if you have a fundamental set, then the general solution is going to be a linear combination from the fundamental set.